Okay, so now we have done resistors in series. Now what will we do? I told you that there are two main ways that we connect the resistors or connect the components in the circuit. One was a series connection, which you saw they are connected end to end. That means the end of the first resistor is the beginning of the second resistor. So end to end connection, and there is no connection between the starting point of first resistor and the ending point of last resistor. You saw, right? So starting point of say R1 was A and the ending point of R3 was D. So they're completely different points. So they are not connected actually to each other, but they are connected end to end. So they're like standing in a line. So they're standing in a line holding hands side by side. Okay. So now this is the example that you can use to remember the series connections. Like if you are standing with your friends in a line and you're holding your friend's hand towards your right like this and the friend's hand towards your left like this. And see, when it is resistors in parallel, the only difference is, you remember when you used to do one arm distance, right? When you stood in the assembly line and the teacher told you to make one arm distance, so you kept your shoulder, so you kept your hand on your friend's shoulder, your friend in front of you. So just imagine you're keeping both your hands on your friend's shoulder and your friend behind you is keeping both their hands on your shoulder. So what have you, how are you standing together? Are you standing in a line like this, like horizontally, or are you standing one behind the other? You are standing one behind the other, right? So that is what is parallel connection, or you are basically standing parallel to each other, right? So your friends, if one friend is standing left to you and one friend is standing to your right, they are not parallel to you. The word we use for that is adjacent or to your sides. These are your sides, right? So your friends standing here in your series connection are to your sides. But in parallel, the friends are standing parallel to you, or they are either in front of you or behind you, right? So that is how you remember the parallel connection of resistors. Okay, so this is what the parallel connection looks like. How is it different from series? It is different because in series, this is one friend, this is the second friend, and this is the third friend. They're all standing side by side. But in parallel, how is it happening? This is one friend, and in the assembly line, the other friend is in front of you, and say one other friend is behind you. So this is how resistors are connected in parallel. So these three are connected like this, and similarly like this. And this can then be like connected to the battery and everything, that remains the same. So I hope you understand that now in case of parallel resistors, you remember in series we said that they're connected end to end. But now these resistors, they're actually having the same ending and starting point. Okay, you might say, no ma'am, look, this resistor has the starting point and ending point AB. This resistor has the starting and ending point CD. So how do they have the same starting and ending point? So then I'm going to tell you, okay, but this point A is directly connected to this point 1, and this point C is also connected to this point 1, and say if you're saying A, B, C, D and E, F, this third one R2, R1, R2 and R3, right? So if you say, okay, they're all connected to two different endpoints, A, B, C, D and E, F. So then I'm going to tell you that A, C and E are all connected to this point 1. And B, D and F are all connected through the wire to this point 2. Now, I would like you to look back to the series resistor. This is A, B, C and D. R1 is between A and B, R2 is between B and C, and R3 is between C and D. So, is there any connection between point A and point D? No, right? There will only be a connection if there was a wire joining A and D like this. But there is no connection like this. A is only connected to B, right? You can say that A is connected to D from here, but it's not directly connected. It's connected to the battery, right? Or A and B are some way connected, A and D. What if about B and D? What if B and D? Are B and D connected in any way? No, right? you go through this path, your resistor R1 comes, then point C comes, and then point D comes. So there is no direct connection between these 2 points. But in parallel connection, you can see all the points to the left of the resistors are connected through some wire to one common point, which is 1. And all the points on the right side of the resistors are connected to one common point, which is 2. So we can say that all resistors are actually connected between the same 2 points. This is a very important 3-star point. Why? Because this is the point that we are going to use when we derive the formula for the equivalent resistance, the combined resistance for parallel. Okay. So you have to remember that in case of parallel combination of resistors, even though it might look like the resistors all have different endpoints, 2 different sets of endpoints, but we have just seen that they are in some way through some wire connected to actually the same 2 endpoints. So we can say that R1 and R2 and R3 are actually all connected between R1, R2, R3 are all connected between point 1 and point 2. Although they look like they've been connected between AB, R1 against AB, R2 against CD, and R3 between EF, but we saw that they're actually all connected between 1 and 2, right? So we've got this clear that all resistors in parallel are actually connected between the same 2 points, or they have the same starting and ending point. Okay. So like your PPT also says that the 3 resistors are connected together between points X and Y. See, all 3 resistors R1, R2 and R3 are actually connected between the main 2 points X and Y. They don't have individual starting and ending points here, here, here or here. Okay, great. Moving on. Keeping this concept in mind, now we will calculate the effective resistance. So, do you remember what we studied about potential difference or the voltage difference? What was it? Potential difference was nothing but the work done to move one unit charge from one point to the other. So, if points A and B, if like 5 joules of work is being done, you remember this formula, V is equal to W by Q, work done per unit charge. So if 5 joules of work is being done to take 1 coulomb of charge from point A to point B. So what do we say? What is V? V is nothing but 5 upon 1 is equal to 5 volt. So this 5 volt is nothing but the potential difference. So what does this tell us? It's between point A and point B. That means that the potential difference is actually this means that the potential difference is actually between 2 points. It's always calculated between 2 points because it's a difference, right? It's not one value. It is one value of a difference between 2 points. So, now think back to what we said in case of a parallel combination. We said that all resistors are actually connected between the 2 points. So now tell me the potential difference across each resistor. Would it be the same or would it be different? Would it be different numbers? It would be same, right? Because they're actually connected between the same 2 points. Look at this. Look at the figure that is given to you, X and Y. So the potential difference is actually between this point X and this point Y. And since all your resistors R1, R2 and R3 are all connected between points X and Y, the potential difference across all 3 is actually going to be the same, right? Whereas in series, you remember what had happened. So this is the 3 resistors, because they are between all resistors are between 2 different points. So the potential difference between all those different points is different. But there, what did we say? The current had only one way to flow. So the current across them was constant, right? So what did we do? We took V1 and V2 and V3 because we saw that because the formula is V equal to IR, right? and if the same current is flowing through each and every one, but the resistance of each and every resistor is different, the V would be different, right? If current is 5, but one of the resistance is 1 ohm, it is 5 volts. If current is 5, series resistor, but the other resistance is 10 ohm, so 50 volts. That is why we saw that the potential difference will be different across each. So we took V1, V2, V3 for each resistor. Potential difference is different for each resistor. But now come to this figure that is given to you. From here, this is the current I coming to you. You show the direction of current like you show the direction of a ray. Okay, you're supposed to show this all the time. Now, like you are walking along this path only. Just think about it. You reach this point X. Do you have just one way to go like it was in series? No, right? You actually have 3 ways to go. 1, 2, 3. 1, 2, 3. These 3 paths you can take. So, because in series current had only one way to go, so the current was the same across each. But now current has 3 different paths to go from. And would the current be the same? Would it get divided equally? It would get divided equally if the resistors had equal resistance. Why? Look here. This is R1, this is R2 and this is R3. R1, R2, R3. I am giving them some random values. Okay, 5 ohm, 10 ohm, 50 ohm. Right? So, just think if you are the current here and you have 3 paths to go. Would you go equally? Would current be able to go equally through all these resistors? No, right? Why? Because the first resistor is going to resist the current somewhat, going to resist it because 5 ohm resistance. The second resistor is going to resist it a little more because 10 ohm resistance. The third resistor is going to resist the current even more because 50 ohm resistance. So, the amount of current that can actually flow is different for the 3 resistors. Okay. So, here actually the current gets divided. So, 3 different currents go here. I1 goes into R1, I2 goes into R2 and I3 goes into R3. So, you remember in series resistors, there was 3 different voltages, V1, V2, V3 because the current was the same. So, here what is different? V equal to IR. Here V equal to IR. We saw the V is same if we want to calculate the current. Okay, I take R to the other side. So, V by R is equal to I. Right? So, what does I depend upon? It depends upon V and R. Is I the same for all resistors in parallel? Yes, because they are connected across the same 2 points. So, V is same. But is R the same? No. R is going to be different for R1, R2, R3 if they have different values. So, I is also going to change because even though V is constant, R is changing. So, I is also changing. So, that means there are 3 different I's for 3 different R's. Right? So, these things you have to keep in mind. You don't need to like remember it like that. You don't just have to like memorize it. Don't memorize anything in physics. Everything can be reached with pure logic. So, what is the logic here that you have to remember? The logic is that in series, current has only one path to go. So, it is the same current that is going to flow through each resistor. So, the V is going to be different because V equal to IR. I is same, R changes, so V changes. But in parallel, what happens? Because the resistors are connected across the same 2 points, we studied that potential difference is across 2 points. So, because R1 is connected against the same 2 points, R2 also and R3 also. So, the potential difference across each is the same. So, what is different? The current is different. Okay. So, what happens here? There are 2 currents, I1, I2, I3. Now, this, like we discussed for series, we said that V1 plus V2 plus V3 should be equal to the parent voltage, which is the voltage of the battery. Similarly, in case of current also, I1 plus I2 plus I3 should be equal to the original current in the circuit, which is I, right? So, we write I, which is the total current in the circuit, should be equal to I1 which is the current that flows through R1, plus I2, the current through R2, plus I3, the current through I3. Now, if I put the V equal to IR formula here, so I is equal to V by R. So I put here V, this is capital V, which is the total voltage of the battery, upon R. Now I'm going to write P here. Why RP? Because we've written total voltage here, so this is the total resistance. That means the equivalent resistance that we actually have to calculate. Okay. Now I1, would I1 be V1 by R1? Would this be V1 plus V2 by R2 plus V3 by R3? No. Why? Because the potential difference of the battery is going to be the potential difference across each resistor, because the potential difference does not change in parallel combination. Awesome. So we remove this 1, 2 and 3 because it's the same. So what happens? This V gets cancelled out from everywhere, right? Or you can say that you took V common here, is equal to V common 1 upon R1 plus 1 upon R2 plus 1 upon R3. You took V common, so you cut V from here. So what are you left with? 1 upon RP is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. That is how you calculate the equivalent resistance in case of parallel. So similarly, let me show you a short video for this also. So here, it's exactly what I told you. One I, that means one single ball of current goes, it gets divided into 3, I1 and I2 and I3. That means into 3 unequal parts, and then it again combines, becomes I1, and this process goes on. So I hope the basic difference between resistors in parallel and resistors in series is clear to you. Okay, great. Let's move on. Okay, so I hope this concept is clear now. Moving on. So this is the same thing that we did. This is just the rest of the calculation in your PPT that we did. So this is the final formula that you get. 1 upon RP. RP is basically the equivalent resistance when resistors are connected in parallel, is 1 upon R1 plus 1 upon R2 plus 1 upon R3. When we solve a few problems, it would become more clear to you. Okay. Great. So the first example says, in the circuit diagram, suppose the resistors R1, R2 and R3 have the values 5, 10 and 30 ohms, which have been connected to a battery of 12 volts. Calculate first part, the current through the resistor. Okay. Okay, so we have to calculate in the first part the current through each resistor. So we'll give the heading for R1, which is resistor 1. So we have to calculate the current. So obviously we're going to use the Ohm's law, V equal to IR. So therefore I is equal to V by R. So now we know that we have to calculate for R1. So what is going to be different? We know that different current flows through each branch. So I1. Is there going to be a different voltage? No, because they are in parallel. But we know there is a different resistance. So R1. So here I1 is equal to, what is the value of V that is given to us? It is connected to a battery of 12 volts. So you can make the given here. I forgot to write the given. You can write the given information. So you can write that we are given that R1 is equal to 5 ohm, R2 is equal to 10 ohm and R3 is equal to 30 ohm and voltage is equal to 12 volt, and then you start your A, B and C parts. Great. So I1 is, what is V? 12 upon R1, right? What is R1? R1 is 5 ohm. So 12 upon 5, which is equal to 5, 2 is 10, 2.4 amperes. Right? Great. So I1 is 2.4 ampere. Now for R2, we have to calculate for each resistor. So for R2, it is going to be similarly I2 is equal to V. What is V here? V is again 12 volts. Because it is the same, upon, you can write the formula again. You can write I2 is equal to V2 by R2. I am choosing not to write now, but it is your choice. If you want to make it more clear, it's actually better if you do. Great. So I2 is equal to V, which is 12, upon R2, which is 10 ohm. So this is simply 1.2 ampere. And for the last part, for R3, we know I3 is equal to V upon R3, which is given to us as 30 ohm. Great. So if I cut this with 2, so this becomes 6 and this becomes 15. So this becomes 0.4 ampere. You can divide it and check. Great. So the first part is done. We have calculated the current through each resistor. Okay, moving on. In the circuit diagram, so this is the same question. We have to now find the total current in the circuit. So do you remember we had written that I is equal to I1 plus I2 plus I3 using the logic that the three currents that are getting divided obviously are coming from the original current I. It is I that is getting divided into I1, I2 and I3, right? Like we talked about the toffee example, the 10 toffees gets divided into 1, 5 and 4. So all of these should be equal to 10, right? Similarly, I is divided into I1, I2 and I3. So I1 plus I2 plus I3 should be equal to the original I. So we just calculated the values of I1, I2 and I3. So total current in the circuit is going to be nothing but I1 plus I2 plus I3. So if you go back to the values that we calculated, they were 2.4 amperes plus 1.2 ampere plus 0.4 ampere, right? So this is what? 4 plus 4, 8, 9, 10. So 1, 0, 2, 3 and 4. So the total is 4 ampere. That is the total current in the circuit. Okay, moving on. The last part says the total circuit resistance. So now we are going to use the formula. We know that Rp, which is the parallel resistance, 1 upon Rp, the formula that we are going to use is 1 upon R1 plus 1 upon R2 plus 1 upon R3. So we need to find 1 upon Rp, right? So we put the values 1 upon what is R1, 5, then 1 upon what is R2, 10, then 1 upon what is R3, 30. So I can see that the LCM here is 30 because 30 comes in the table of 10 also and 5 also. Great. So I write 1 upon Rp is equal to, I take the LCM as 30. So 5 into 6 are 30. So 6, 10 into 3 is 30 and 30 into 1. So this is 6, 7, 8, 9, 10. So 1 upon Rp is equal to 10 upon 30. So we had to find 1 upon Rp or did we have to find Rp? We had to find the Rp, right? The total resistance of parallel. So what do? We take the reciprocal of this equation. So we do Rp is equal to, this again goes to the denominator and this goes to the numerator, this comes to the denominator. So 30 upon 10, which is nothing but 3 ohm. Okay. So we have calculated the total resistance in the circuit also. Moving on. The next example says, okay, so this next example says that in figure R1 is 10 ohm, R2 is 40 ohm, R3 is 30 ohm, R4 is 20 ohm, R5 is 60 ohm. So we just quickly write, I'm just going to start from here because I might not have a lot of space there. Given R1 10 ohm, R2 40 ohms, R3 30 ohms, R4 20 ohms and R5 60 ohms, and we are given V is equal to 12 volts. Great. So the first part says calculate the total resistance in the circuit. So now I want you to analyze the circuit. What can you see? This part that I am highlighting, in this part I can clearly see that R1 and R2 are connected in parallel, right? They are parallel to each other or one behind the other. And here R3, R4 and R5 are connected in parallel to each other. So we are actually going to calculate their equivalent resistances separately. So what we do, we first calculate what will be the equivalent resistance of this pair. Okay, so let us say that let equivalent resistance, I'm writing it in short, you write it completely. Let equivalent resistance of R1 and R2 be equal to R12, right? So here 1 upon R12, we can represent it in any way. You can write 1 upon RP also, but 1 and 2 are also in parallel, then 3, 4, 5 are also in parallel. So I don't want to use RP for both of them. So I am using R12 here, and for that I'll use R345. So you can use any notation that you like. So what is the formula? 1 upon R1 plus 1 upon R2, because here there are only 2 resistors. Okay, so 1 upon R12 is equal to, what is R1? R1 is 10 ohm. What is R2? R2 is 40 ohm. Great. So 1 upon R12 is equal to, what is the LCM? We know 10, 40 comes in the table of 10. So 40 is the LCM. 10 into 4 is 40 and 40 into 1 is 40. So 1 upon R12 is equal to 4 plus 1, 5 upon 40. So the only thing that you have to be very careful about when parallel combination you are calculating is that it is in the denominator. It is actually the reciprocal that you have to take at the last step. Don't take R12 is equal to 5 upon 40. No, it is 1 upon R12. So you have to do the reciprocal of it to get R12. This is the mistake that students mostly make when it comes to parallel combination calculation. So keep that in mind. So if we take the reciprocal of this expression, R12 goes to the numerator, 1 comes to the denominator. So it's R12 upon 1 is the same thing, is 40 upon 5, right? So 5 8s are 40. So R12 is 8 ohm. Great. Now we calculate then we say let equivalent resistance of R3, R4 and R5 be equal to R345. Now you could have used R12 in place of R12. You could have said R, and here you could have said R dash, or R12 you could have said R dash, and this you could have said R double dash. So whatever notation you like. So here 1 upon R345, I am using 345 so that this is the first question, one of the first few questions you are doing. So I want it to be absolutely clear to you that okay, we are considering these two separately, then we'll combine them. So right now what have we done? We calculated what will be the equivalent of R1 and R2. Now we are calculating what will be the equivalent of R3, 4 and 5. So it is 1 upon R3 plus 1 upon R4 plus 1 upon R5, right? So 1 upon R345 is equal to, it is equal to 1 upon, what is R3? It is given to us as 30 ohm, plus 1 upon, what is R4? It is given to us as 20 ohm, and what is R5? If it is given to us as 60 ohm. So 1 upon 60. So I'm going to remove this given part. Okay, I hope you have written it down. If you hadn't, just go back and write it. I need some space here, so that's why I'm removing it. Okay, so now here I am going to do the rest of the calculation. So we know that 30, 20 and 60, what is the LCM? The LCM is 60. So we write 1 upon R345 is equal to 60 is the LCM. So 30 into 2s are 60, 20 into 3s are 60 plus 1. So 3, 4, 5 and 6. So this becomes 6 upon 60. Again we take the reciprocal of this and this. So it becomes R345 is equal to 60 upon 6, which is nothing but 10. So this is equal to 10 ohm. Now I'm going to remove all of this. So just pause the video, just take some time, write all of these calculations down. understand it, because the next step that I'm going to do is very important. Okay, till then I'm just removing all of this. Okay, so now if you remember, this circuit gave us the equivalent, not this circuit, sorry, this R1 and R2 parallel combination gave us the equivalent resistance of 8 ohm, and this part gave us the equivalent resistance of 10 ohm. Now, what does equivalent resistance mean? If you remember, when I was introducing parallel and series combination to you, I told you that it is important to know the equivalent resistance because it's difficult to work with 4 or 5 resistors instead of just one resistor. So that is why we calculate the total resistance of those resistors. So what are we actually doing? In case of series resistors also, we are calculating the equivalent resistance, which means that whole series combination can be replaced by that one resistor with the equivalent resistance. Similarly, in parallel combination also, when we calculate the equivalent resistance, that equivalent resistance is the one resistor that can replace all the other resistors that the equivalence was calculated from. What did I just say? Must have sounded confusing. It means that this segment, we calculated the parallel equivalent resistance as 8 ohms. That means R1 and R2 can be replaced by just one resistor, which is 8 ohms, which is their equivalent resistance. Similarly, here we have our battery. I'm just making one cell because I just want to make my work less. This is plus and minus. Now, this R3, R4 and R5 combination, we calculated their equivalent resistance to be 10 ohm. And that, what does that mean? All three of them can be removed and can be replaced by just one resistor with the resistance of 10 ohm. Right? Now look at this. Now look at this carefully. Are these two resistors in series or are these two resistors in parallel? Think about it. Whenever you are confused if resistors are in series or parallel, just draw the path of current. So here what would the path of current be? Current goes from the positive, goes through resistor, this resistor, comes out, doesn't have any other path to flow from, comes from here, comes here, goes through this resistor and keeps circling. Did the current get divided? No, that means current through both the resistors is same. Was this a property of series combination or parallel combination? It was a property of series combination, remember? Because in series we said that current doesn't have any other path to go, so it just keeps flowing the same current through the resistor. So this should make it clear to you. Now you will write a line here as same I flows or can be seen to flow through both resistors. So this was what our R12 and this was what our R345. Through both R12 and R345, they are in series. That is why we didn't calculate total of R1, R2, R3, R4, R5. We can't do it in one step because we can't see clearly if these two sets are in series or parallel. That's why we only calculate the series resistance or parallel resistance of the parallel resistors that are clearly visible to us. It was very clear that R1 and R2 are in parallel. Okay. It was very clear that R3, R4 and R5 are in parallel. Okay. So calculate their individual resistances, replace them by their equivalent resistances and then see if those equivalent resistances are in series or parallel. So here you have seen, you can either write this point or you can either write that we can see that they are connected end to end. Thus, they are in series. So, final equivalent resistance in the circuit, or you can write RC, which is the final circuit resistance. C for circuit is nothing but what is the series combination. What is the equivalent resistance? It is R1 plus R2. So, here R1 is R12 plus the second resistance is R345, which is equal to 8 plus 10 is equal to 18 ohm. Okay, that is your first part. Now, what does your second part say? Your second part says calculate the total current. So now if this is 18 ohm, what does this mean? That this series resistors, this two series resistors can be replaced by just one resistor of 18 ohm. Let's do that. What is our purpose of doing all of this? It is just to simplify the circuit. Now look at this. This circuit becomes, so R1, 2 here and R3, 4, 5 here. Both can be replaced by just one resistor RC, which is connected to the battery, to the key or whatever, and like this. On the ammeter also. I have forgotten the ammeter. Just draw it. It doesn't matter that much because it doesn't affect the reading in any way. So what have I seen here? R1, R2, R3, R4, R5. A 5 resistor circuit is replaced by just one resistor. So is it going to make your calculation easier or not? Calculating everything. So if the current was different, I1, I2, I3, I4, I5, 5 currents, and here just one current. So this is the purpose of doing all of this work, applying all of these formula to have a simplified circuit. That's what we want to do in life. We want to make life easy, right? So that is what we are doing, and that is why we are doing it. If someone wants to ask the question, why do you have to apply so many formulas? Use your original circuit. Okay, do it. You're going to get stuck somewhere or the other because there are 5 resistors that you have to calculate for. So make your life easier. Use these formulas. Okay, so we come to the second part. Now what have I done? I have replaced these two resistors by their equivalent resistance, which is 18 ohm. This battery is of 12 volt. So we apply simply V equal to IR, which is I is equal to V by R. So I is equal to what is V? 12 upon what is our equivalent resistance of the whole circuit is 18. So 2 6 are 12. 2 9s are 18, 3 2s are 6, 3 3s are 9, which is equal to 0. So 0 point, which means a 0 gets added here. So 3 5s are 15, 3 6 are 18. So 6 and 18. So 20 was here. So 2 is left. So around 3.66 or 3.67. That is your reading. Okay. So this is your final answer. 3.66 ampere, or you can write it can be 3.67 because it's going to go on like 3.66666. So you just round it off to 3.67 amperes. That is your final answer for the current flowing in the circuit. Okay. So I hope this question is clear to you because this question used both the formulas of parallel and series. It had the simplification part where we simplify each circuit by replacing all the resistors by their equivalent resistor. So this is a very important question which covers all of the topics. Okay, great.